And Brad yelled at me. No, he doesn't yell at me. I do all the yelling here and in my house. My dog knows WTF. I'm not kidding. Like if I say, they both like to go and like sit on the couch because that's their timeout zone. Like they know they have to go timeout. All right. Did I record that? I did record that. Okay, great. Whatever happens in control class, it stays in control class. All right. I think we're missing a couple of the usual students that show up, but they're not here. Hopefully they will show up eventually. So I did change the way that I was gonna teach a little bit. So I'm still covering everything in the book. I just move things around. So sometimes we have to move from chapter 4, 5 to like 4 to 6, 6, then back to 5 or so. Follow along with the book. The reason I'm doing is, for example, chapter 4, if you're following along, it starts with something like high level and then explain an example, then goes and explain what that was. So I'm going to explain what that is. So when you start chapter 4, it will make sense to you. So you will find everything in the book, different orders. Also, how many of you actually look at the book? So I don't know if you know this or not. Exam 1, 2 of it, the 2 problems were in the book. I just changed it slightly. So they were solved problem of the book, special problem 2. The first was the other way around. That's the only difference. So look at the examples, just review them in general as we go. All right, quick review of open loop system. Do you see it? No, you don't see it. There, now you can see it. So quick review of open loop system. So as you can see, I'm adding more items to the system because now you know more about them. So case 1, so you see a block diagram and a flow diagram, right? Block diagram on the right, flow diagram on the left. You should be able to understand both of these. They are the same. I will go between them when I'm solving problem. I try to always give you the block diagram, but if it didn't, the flow diagram, you can easily convert it. All right. So for an open loop system, we have always our plant, right? We have an input, we have an output. Can we have a controller in our open loop system? So controller plant, then it goes input and output. Drew says yes. Why? And then someone said no. We're gonna go and talk. Why I can't have controller?
Actually, now I'm thinking no.
Okay, who said no? Why? Well, so there is no feedback. So the system is open, right? Now, does the controller means that you have to get a feedback from the output to control something? No. You can have a timer, right? That does something in your system like dishwasher, the what is the sprinkle system, sprinkle system, right? There's a timer, David. There's a timer, okay? So a timer, which is your controller, plant, input, output. So you don't necessarily have to not have the controller. It's just not closed. So there is no feedback from the output going back to the input to compare things. Now, you could have a couple of things when you have an open loop. When you have a system, when you have a process, it means that you have an environment, the other Drew. What kind of input we would have when we are dealing with environment? So we will have input that the force that once, like on purpose, we apply to the system, right? What kind of other input do you think we will have in our system in case of open loop? We will have noise, not error. When you say error, you're already in your mind compared to things, right? So it's not error, but it's noise. So when you have a system, you could have noise. Noise from the environment, where your process is, when your system is, right? What are they? Why do we have those noises in our, when we have a process or we have a system? Something in the system changes, right? So your book has an example of like a rolling mill. So at the beginning, the system is empty, there's nothing. Then it rolls steel at the beginning. When the steel starts going, there's like a shock to the system, right? There's an input force that is the noise of the environment, is not the actual force you wanted. Or sometimes something in your system changes, breaks a bearing, or something in the system, the transfer function of the system was estimated. Now the actual impact of it is apparent in the system. So we can take care of all of those with noise, right? So noise will look like an input to our system. So as you can see here, so RS here, we usually show the actual input or control input with R, just as to make sure that whenever we saw R, that's the actual input of system. You will see also disturbance. Usually we show with T sub D, T disturbance, right? Again, you can change the signal name, but make sure that you're consistent through what you're using. This is also like an input to our system. Now, this disturbance can be because of the process, can happen before the process. Now, sometime in your system, you have a controller, then you have a process. This noise is not from the controller. It's usually from the environment applied to your process. So it usually appears around where the process is. The control is something you design. You don't design something that has noise. Does that make sense? Usually the control, if it's digital, it's a bunch of numbers. If it's analog, you pick the values such that it will meet your requirement. So you're not adding noise to them, right? So in a system, to identify this noise, which is called process noise, you want to check around where your process or system is. It always shows as an input, all right? It can act as an input. Do you remember superposition? In LTI system, we have superposition. This is LTI system, right? So if I want to see the effect of noise on my system, I could say, let's think R is 0. I don't actually have an input. I only have this noise as an input and see what's the effect. Then say, okay, let's say that we don't have a noise. TD is 0. And let's just see what's the effect of the system with just R being the input. And we can add them together because superposition holds in LTI system. That's literally what we do when we deal with noise. Now, or here we'll call it disturbance because it's disturbing the process of our system. Our goal when we design the controllers is to reject disturbance. So we design our system such a way that if there is a noise, if there's a disturbance coming from outside, our system would reject it. So now how do we know? Well, we study our system when we are designing our a controller, or even when you're picking a motor, you're thinking about all the threshold, right? What if this and this happen? So this and this happen. One of them is the amount of disturbance your system will receive, and you foresee that in your design. Okay, so that's one way. Just we can reject our disturbance basically using our system design. And if it was designed already, you pick a motor from a shelf, you know, off the shelf, you buy stuff, then you can design your controller in such a way that it would reject disturbance. Make sense? So from here, we're kind of going into realm of controller. So you're kind of like, this is where the course starts. It starts first with identifying what kind of inputs we have, what exactly our system is, and what's the role of our controller. So that will be for your open loop system. Now, if we have a closed loop system, we can introduce another element to our system. So in a closed loop is the same thing. We will have a signal from output back to input and compare, right? A lot of times, in reality, you need a sensor to read that for you, right? We can show our sensor using a transfer function, and that transfer function is in the feedback loop, correct? Now, depending on this resolution of your sensor, you will have some noise, right? Those are called noise measurement. And because you don't have 100% high, like you don't have a true sensor. There's always some error, but the amount of error could be so low that you can sometimes eliminate them. Or there is some error that you can actually have to see them when you're designing your controller. All right, so you need to know what kind of controller you're, what kind of sensor you're picking. That comes to picking component. What's the limit that you will have when you're purchasing your sensors? Money, right? So you pay less, you have to compensate it. Thankfully, we can do digitally. We can design a controller to compensate for that. We could see the noise measurement. Usually, sensor come with the accuracy or resolution. There are some numbers that you can use and see for the amount of inaccuracy in the system. But you have to consider those when you're designing your controller, right? Usually, you'll see that in the feedback part of the loop. So here, and NS, you could call it DM, TM, whatever you want to call it, a signal that appears in the feedback loop, and that's measurement noise because of the sensor you have. Now, when we do unity feedback, what we're actually doing, what we're assuming for unity feedback. What does unity feedback mean first? Yes. So why do we give value of 1? So this is H of S, right? This is a sensor. So let's say the transfer function H of S is 1 over something, right? And this is basically like, hey, this sensor can show me, so this signal is YS times HS. Agreed? Reading times that. Now, unity feedback says HS is 1, right? So in your unity feedback, whatever you have here, I don't really care about that right now. You have something like this. So if you only have the signal, it means that this actually is 1, right? The signal is Y. So if H of S is equal to 1, you have the whole measurement, the whole actual output. If you're missing resolution or quality, H of S is less than 1, right? Transfer function, output to input, so if it's less than 1, you're not actually getting everything that you asked for. So you get 99% of it, right? So your sensor, at best, at ideal, has a transfer function of 1. So when we are doing an analysis, we can say, okay, let's imagine we're using ideal sensor. So whenever in a problem, we say ideal sensor, that's what it means. Feedback is unity. So I'm getting 1 to 1. I'm getting 100% of my output. The reason is that we are not spending time on thinking, okay, what is the accuracy of sensor? We're designing the controller for ideal system, then we run it and see how much the sensor impact, because you can pick different sensors. So when you solve a problem, you don't want to have too many variables. So that's one way of getting rid of that. So when I pick a unity feedback, then I'm like, my sensor is perfect. Do I have a measurement noise? No, because I said my sensor is 100% perfect, right? So there is no low quality, low resolution, anything into it. So in reality, we don't actually have unity feedback. That's just for analysis, but it just makes our life super easy, right? The only difference when you're in reality, it has a transfer function. You just put that transfer function in all of your equation. That's the only difference. Sounds good? Awesome. All right. So this was review. I didn't previously went too much in detail in noise and input. I thought this is a good place to do it before we jump into the rest of our topic. The next thing, this is also review, but I thought I would just talk about it. Friday, we talked about effect of pole and zero on system stability, right? So pole, they have the main, they are the main factor on the stability. So if in what cases you have a stable system? Yes. Or poles on left half plane, right? So But we said that if there was a zero near to one of our poles, it could change the behavior. It doesn't mean that zero will impact the stability. It can change the behavior, even a stable system. Now, so when you have a stable system, if you have, let's say, first order system, or in general, stability means your system will start, if you apply a disturbance to it, it will start moving, but eventually will settle down. So it will reach to balance with stability. So it can from top down, depend on what your input is, it will eventually goes to a steady state. That's a stable system. Sometimes you have a neutral. So look at these two, like they should be a good demonstration of what a stable system is, right? So if I move that cone a little bit, I like wedge it a little and let it go, it'll go back to where it was, right? If the weight is enough, it'll go back to where it was. Now, the system is stable. If I move this guy, the second one, if I roll it, it will roll, but it is still in the same shape, same condition. These are neutral systems, right? So the environment, the force, the input doesn't change them. Their state, they stay the same wherever they are. The other one though, is your unstable system. It's like the inverted pendulum. Have you seen inverted pendulum on the cart? The cart moves and this thing tries to balance. There's just one balance point. Everywhere else is unbalanced. You have to control it for that one point. Okay, so but if you apply a disturbance, if that system is not controlled, it will fall into an unbalanced state. So this is how it is, we can represent it to remember. This is what a time response of that would look like. So anytime you plot something and your response did that or did this, some of you did your CP5, CP15, your solution looked like this. I looked quickly. If that's what you got, this unstable system, right? It's not controlled. So if that's why this is good to know. If you get this while you were trying to control the system, what does it mean? You went wrong somewhere. Maybe your code was wrong. It doesn't mean your controller is wrong. You might have written the code wrong. If your code is right, then your controller needs adjustment. All right. So we kind of use this as behavioral study of our system. I know if I get, the only thing you want is probably the one on the right, the stable, controlled, settles down. Because the one in the middle does not need a controller, can't change it. And this is bad, juju, right? You don't want to do this. So in S-plane, again, it is important to know which domain we are talking about. If our poles are all on the left half plane, we are stable. If at least one pole in right half plane unstable, and we have the case of marginally stable. If poles of the system are on the imaginary axis, we are marginally stable. Why? Because any disturbance, anything from the environment, any noise might shift the system slightly and is already in the right side. That's why this is very marginal. So if you happen to be on this imaginary axis, it's not unstable, but it's also not stable. It's not a good place to be, but sometimes when you're designing control, you're kind of shifting your system. So if you're getting close to imaginary, it's good news. You can shift a little more and then the system will be stable. From this, you should also conclude, I probably don't want to be really close to this axis either, right? When you're designing a controller, you want to make sure the poles of your system are shifted kind of to the left, right? So with some disturbance from the environment or noise in the measurement, you don't go to the right side. So you want to stay away from that. These are factors that decide your choice of controller or the coefficient of your controller. You want to stay away from this region, all right? But again, since it is a process, being near the axis is not a bad thing. And sometimes you might have to be there, you just have to account for other things in your system, all right? So you should basically be very comfortable with looking at the block diagram and being able to draw your S-plane and understand what would the time response look like. So if I have my poles in here, I know I will have, so if there was a pole on the right side, I know my system probably gonna be like, I don't know, so at some point I'm gonna eventually get somewhere in a very long time, but it's going to be very oscillatory because I have two major poles on my imaginary axis. When we get to root locus methods, you will see that you place poles on the left-hand side and you're grabbing your whole system and moving it to the left. The behavior of your system will change. All right, those are the exciting part, I think, for designing controller, because you can visually see it. Now, these are all kind of an introduction to error signal analysis for a closed loop system. So we are going to deal with closed loop system from here, all right, because we are dealing with feedback. Whenever I say error, so there is a feedback system involved. Now, assuming our system is stable, right, means that all the poles on the left-hand side, we are going to write the transfer function, let's say is y over r, and we want to find error. You know that error is the difference between your input and your output. Your input, now, if it's control input, is something that you want, you desire, and you're trying to set to that value, right? There is a reference input and an input, like a voltage to the system, or I want to go to this angle. So this is to that angle, that reference input that you're trying to control and achieve. Now, to write the error, I can write r minus y. Now, from this, what is the transfer function of this system? Someone quickly. I heard G over 1 minus GH. So the output is basically G over 1 minus GH times RS, right? Plus, yes, plus is not minus, plus because of this guy. I heard wrong. Someone was wrong. I'm always right. Of course, I'm a teacher and a woman. What do you expect? You're all wrong. You guys are right. We are the same species. Yeah. Okay, so now I can replace y and see what I get. So error is r. I'm gonna just skip all the s's. G over 1 plus G H R. I'm going to factor out R. Why am I doing this? Because I want to see the error and to see how does the error changes with my input and my transfer functions. That's why I wrote it this way. You might say that, hey, why didn't you write R based on Y? Well, what would I get? I would get the input, everything based on the output. It doesn't give me much of information I'm looking for. So that's the only reason. I want to see how the error changes based on the input and the transfer function. Now, here you see that I can even go further if you want and say 1 plus GH minus G, 1 plus GH, or it does not matter because this is a function of G and H, right? Now, looking at this, we will see that the error of a closed loop system depends on your input and the transfer function. The transfer functions in the system, right? The system itself and the input. So you can, if you cannot control your system, you're controlling the input, which is a control problem. By controlling the input, you can get what you want. What do we want this error to be? Huh? Small, 0. Ideally 0, but usually your goal is to drive this value to 0, right? Or very close that you can not consider it and say, okay, I'm fine with that. Now, to make things simple and see how input will impact this, I'm going to check all the unity feedbacks. What does that mean? To have a unity feedback? What's that? On the feedback, h of s is 1, right? So the gain of h of s is 1. So now if that is 1, look at that relationship. It would only depend on g, the transfer function of your system and the controller you have, and the input. So for analysis, that's better because I'm saying that, hey, let's say I have ideal sensor. I'm not going to deal with that. So for a unity feedback system, so this was that h. If you put that value, h equal to 1, your error becomes 1 over 1 plus g of s r of s. So it only depends on input and the transfer function of your system. Now, if your controller is there, convolution will multiply, right? So your plant and control becomes the GS. So the steady state error for unity feedback system, we can say, so since we are saying steady state error, what does it mean? What does it mean to find a steady state error in English?
The final value.
So the final value is not error, is the final value. What's the steady state error? Close though, but need to complete.
The error when the system reaches.
The amount of difference or error deviation you have from the final value desired from the final value you have. So when we say steady state, you're sending time to infinity, right? At the end, when the system settles, you want to see how much difference it has. If you plotted and you had a steady state error in your system, let's say this was a step input, your step input gain was 1. Sorry, that 1 is going to be here. This is 1. And no matter what you did, you always have this error. The final value always has an error with respect to your desired value. If you're using a step function, your desired value is 1, right? If you just unity step, sorry. So we are trying to find that out. So that's the steady state I'm trying to figure out. That we want it to be 0, right? That's ideal. Or we wanted to minimize it. So in order to minimize something, first you need to know what it is. So this part, we are trying to figure out the equations or transfer functions, however it's not a transfer function, it's the equation or relationship. It's a relationship for your steady state error. Then we can say, how can we make this 0 or go towards 0, all right? So if you remember from before, so sending a value to infinity in time is equal to sending that s in s domain to 0, right? So I can say, since I'm using a, well, I'm not going to do that yet right now. So I can write limit s e of s, which my e of s, which is this a of s, you will see why I had to drop a. I realized after I created everything and then I had to redo everything. So this thing is E of A, right? So I'm trying to see what's the value of this thing at time infinity. So when you look at this, you see that, this looks like my final value theorem, right? So using a final value theorem, you can evaluate, because in that you also find what's your final value. And you say, hey, where do I want to be? Am I close? Am I at the final value? If you're not, then you have some error. So if you look at here, the error depends on your open loop system transfer function, right? Plus the choice of input, R. Why? Because I'm only dealing with unity feedback. So if you have unity feedback, your error depends on the open loop transfer function, meaning the transfer function of if you have a controller and the system itself, and what's the input. You don't care that this is a closed loop system, because we already applied all of this. All right, so let's see what will happen for some of our familiar inputs. So what are those inputs? What inputs usually we can apply when we are trying to design a controller? Step input is one of them, right? So do you remember that there are some inputs that we usually use them to see the response of our system? In CP15, you used impulse. Previously used a step. So I'm going to introduce a few more of them today. Step is the first one. So if I say, okay, I'm gonna see the error, steady state error of the system if the input was a step, then whatever I get will depend on only what? The error depends on two things, the transfer function of the system and the input. If I say, let's say, for example, try step input, then whatever I find out depends on what? The transfer function, right? So I'm kind of eliminating things. So I'm using familiar thing. First, I said, let's replace the sensor with a feedback, unity feedback. Let's assume the system is ideal. Now I'm saying, let's assume my input is on a step input, right? So I'm focusing on transfer function. Why am I telling you this? Because this is the process of solving problems. If you have 3 or 4 things you don't know about, you will start defining or assuming things, right? And then you have to write down. So if you can follow the train of thought, you can always work backward and change those values back. So I'm going to start from unity feedback. So H is 1, step input. So R of t is 1t for unity step input, A of t for a unity, for a step input, right? And then I want to know what is my steady state error. So step input. So if I have RT is 1t, this means what? That's a unity step. You say unity when this value is literally 1. All right. But here I'm using A, so it has a gain. So if I plotted this would be, this was in time, it would be A. Right? So kind of a bit like generally what it would look like. In time domain is AT, in S domain would be A over S. Why? Because this one in S domain is going to be 1 over S. These are the conversion you want to remember or be comfortable with, so you don't have to look up the table from time to S domain. All right, so from before, I know my equation is this for unity feedback. So limit of S, R of S over 1 plus G of S. So let's replace them. So limit of S, R of S is A over S, 1 plus GS, then S goes to 0. So here I can cancel these 2 out. So ESS would be when S goes to 0, A over 1 plus G0. Right? So this means that the error of transfer function depends on the transfer function of the error of closed transfer function. It depends on the transfer function of my open loop or the actual system, right? When S goes to 0, which is when T goes to infinity. So when you have a unity feedback, when you have a step input, you can expect a constant value for your steady state error. So you will have a steady state error usually when you have this case, and it's not good because you don't want a steady state error. Your goal is to drive that to 0, right? So we will choose our G in a way that we can drive this value to 0. Right? So just by looking at that, how can we drive that to 0? Was very big, it was infinity, right? There are ways to do that on purpose. You can choose the control in a way that drives that to infinity, a over infinity 0, and you're good. But once you have this understanding, designing control is easy because you exactly know what you want to do. You just need to know what makes this goes to infinity. That's the only thing you need to know, and then you're done. Okay? There are ways to do that, and that's like you will learn those, but this is important. If you don't know that's what you want, you can't design the controller because like, what are you trying to do, right? So this is case number 1 when you have step input. That's why it's important. Let's see what's the response of a step input, right? Do I have a steady state error just because of the system? Most of the time, yes. And you need to do something for it. Next, it's ramp input. I don't know if I talked about this or not. Have I talked about ramp input? Maybe I did. Okay. So ramp input in time domain, you have a line that shoots over, right? So that's your R of t is A times T. So A is again your gain, all right? We are still using the same unity feedback system. I didn't draw it, was the same block diagram as before. Now, for this one, I'm just going to write that equation. Steady state error is going to be limit of S RS over 1 plus G of S. When S goes to 0, RS. So here is the limit SA over S squared, because that's what in time in S domain is 1 plus GS when S goes to 0. Now see what happens here. ESS becomes limit of A over S times 1 plus G of S. Correct? Now, I'm going to expand this just to show you something. Limit of A over S plus S G of S. When S goes to 0, this guy is 0, right? Here, what kind of solutions I can get? First, what does the error depend on? When S goes to 0. Depends on the transfer function again, right? Because, so the error is A over SGS, right? So if SGS becomes 0 somehow, what would be the value here? Infinity, right? If SGS is not a 0, is a non-zero value, you will have a constant value, right? 0 is also a constant value, constant. We don't know which one until we know what's the transfer function, right? So meaning that going backward, when we know the transfer function, we know what would be the error if we had a ramp input. There are 2 cases. We can get infinite error. What does infinite error mean in terms of stability? Unstable, right? But we have a way of making that system stable, which falls in the second part. We want it to be a constant value. 0 as a constant value is great if you could do that. If not, we could always limit it to a number, right? Then we have to manipulate the transfer function. Controllers do that. You define, you place that S somewhere, 1 over S, S cancels out with S, and then you have your G of S. If G of S is like a value, then you're good. Does that make sense? So that is the process. Again, we are always working backwards in this case, because we usually know what we want. Well, we should know. If we don't know what we want, then that's just a loss. We usually know what we want, and then from there, we want to see what we can do to get that. That's always how you design controller. Sam. No, you're James, you're not Sam. Sam is over there. Sorry. It's okay. I just call your names and then you pay attention. It's okay. So this is the second case, right? When you have ramp input. Yes.
So why is it not a divide by zero error? If F equals zero?
But sorry, I didn't.
Why is it not a divide by zero error? Or like an undefined,
Which one is undefined?
like when S equals zero and that bottom is equal to zero.
So because you don't know what this G of S is, if this was 1 over S plus 1, this was S, is cancel out. It would be 1 over 0 plus 1, so it would be A over 1, it would actually be A.
Okay.
You can make it also such that it will be infinity, 1 over infinity, 0, 1 over like,
Okay.
right? Because we don't know what is in transit. Now, in your exam, you saw, what does this represent? Integral, right? So you can always add integration to your system, which is a pole at the origin, right? 1 over S. Correct? So that's how integration is. So by adding an integral to your system, you can get rid of some of those things you don't like. That's the integration part of PID controller, basically. All right. So I don't want to start, hey, this is PID controller. Now let's design a PID controller. We are starting with what we want. How does it look like? Now, when you see PID controller, it's going to be S plus 1 over S plus something. And it's like, oh, okay, that's a 0, that's a pole. And the other one is just error of something. That wasn't hard. So we are doing like very fundamental. When we get to PID, the definition or the concept should be, oh, I already know that. I just need to design now. Okay. So this was out of, but this is a good question. So maybe I should have just brought an example. The next thing I want you to see is the parabolic input. And that's the last one of them. The only difference is, so the equation of parabola is a t squared, and then it in S domain is a over S. How do you say to the power of S? Cube. Okay. A over S cubed, right? So we write the same equation and see what happens. ESS is the limit of S, R, 1 plus G of S, right? R here is A over S cubed when S goes to 0. So I can cancel one of this and do the same thing. Again, I'm just here observing what is happening. We don't know what our system is, and it really doesn't matter. As long as we know what is happening, we can put any system, which is your fast participation, by the way. So this would be A over S squared plus S squared G of S when S goes to 0. So this one is 0 no matter what. Here, again, depend on your GS, you could have different cases. You could have a constant value or an infinite value. Infinite, unstable, we don't want. Constant, better. We want that constant to become a 0. If not, drive it to the minimum that is acceptable by the system. So this is a quick way of knowing, even without running any of those tests in MATLAB and building, what kind of error I'm dealing with. What should be the characteristic of my system? So I would expect an error of 0. Does that make sense? Because from this, you can say, if you had the transfer function, you should be able to tell me what's the error, right? You just plug in, all S's are 0. You just like a simple calculation, and you should be able to say, I would expect this system currently give me this error. So I know if it's 0, good for you, you don't have to eliminate. If it's not 0, you have to eliminate. If it's unstable, well, you have your work cut out for you. So like the whole enchilada. All right. Make sense so far? Great. I don't think we will get to sensitivity. It's a good example, but you need to be like 100% here. I feel like you already lost you half an hour ago. So I will keep this one for Wednesday. But for class participation, you could use what you learned so far, or if you didn't, go back and check the lecture so you'll be able to do class participation. The passcode is